We have another example problem here. On a 30-degree Celsius day, there is an explosion. The sound is heard 3.4 seconds after seeing the flash. How far away was the explosion? This is along the same lines as lightning, so where we sometimes count 1 1,000, 2 1,000 between seeing the lightning flash and hearing the thunder. So the sound, because they've given us a temperature, we're going to find the speed of the sound using the equation 331 meters per second times this quantity where we have the temperature in Celsius plus 273 and divide by 273. So we can figure out how fast the sound is traveling. Now, seeing the flash, well, we see light. So the speed of light in air is essentially the same as the speed of light in a vacuum. So we know how fast the light is traveling. This time that they give us is the delta t, meaning the difference between how long it takes for the sound to reach us minus how long it takes for the light to reach us. All right, so these speeds are constant if we assume the air is the same temperature and everything between where the explosion happened and where we are as the observer. So since the speed is constant, we can say the speed of either one is going to be the distance either one travels, so the distance the sound travels, or the distance the light travels, divided by the time it takes to get to us. So this tells us that the time either one takes, light or sound, to get to us is equal to the distance the light travels divided by the speed of light, or if we're talking sound, the distance the sound travels divided by the speed of the sound. Since we're given this difference in time, I want to set up the equation that represents that. So we are given the difference in time. So how much longer it takes the sound to get to us compared to the light. Since the time it takes for sound to get to us is going to be this distance from the explosion to us divided by the speed of sound, the time it takes light to get to us is going to be the same distance because it's the distance from where the explosion occurred to us as the observer. And we'll divide by the speed of light, which let's just leave that as c. So in either case, they're traveling the same distance. And this distance is what we're looking for. So we can say this distance is the difference in time divided by this 1 over the speed of sound minus 1 over the speed of light. Now, you might be recognizing that the speed of light is so large that we essentially hear it at the same time it happens, which is true. So I'm going to show you the answer, including the speed of light, where I have the equation written already, and without. So 1 over, I guess I need to calculate this sound. So let's go ahead and plug in the 30 degrees. So on this 30-degree Celsius day, I'm finding that the speed of sound 348.713. So that's the value going in here. And I'm actually just keeping the value in my calculator and using that. Speed of light, 3 times 10 to the 8th. So when I do put in the value, including the speed of light here, I get 1185.625, which of course I cannot be that accurate. We're gonna assume a number like 30 degrees Celsius is exact at that second decimal place. So we have 2 sig figs here. So I would write this as 1.2 because we have to round that 1 since the 8 is the next number. 10 times 10 to the 3rd meters, or 1.2 kilometers. That works great as well. If I go ahead and say we essentially we see the flash at the instant the explosion takes place. So essentially this term is not infinitely large, goes to 0 because it's so far away. There's no significant amount of time between us and the explosion as far as the light is concerned. If I do that, where I say essentially that the distance is simply the speed of sound times the time difference, I get 1185.624. So yes, it is totally okay to consider the light, the flash that we see, is happening instantaneously, since the speed of light is so incredibly large. Either way, we get the 1.2 kilometers. So this explosion happened 1.2 kilometers away from where we were. The idea is the same behind trying to estimate how far away lightning strikes. We can assume we're seeing the lightning instantaneously as far as the wave, that light wave traveling to us. And that's why if we represent and count the time between the lightning strike and when we hear the thunder, we can figure out how far away it is.